Hey everybody, I wanted to go ahead and walk through basically the kind of overview of what is an effective way to do the practical final exam. So as I demonstrated in the previous videos, the collection of two data points, I wanted to go ahead and provide you with more or less the overview of how to collect several future data points. So the data points that we got were from a 10 microgram per microliter sample that was 0.519. Okay. And then we had a sample with an unknown concentration. U and K is what I will label that, unknown concentration. And that was 0.506. Okay. Now, those two data points are really close together. And I think what I would want to do is I would want to empty out the cuvette from my unknown and repeat this maybe two more times. And so that means empty out the cuvette, add 900 microliters of the Bradford reagent, add 100 microliters of that unknown, get the measurement for that unknown's absorbance a total of 3 times. And that doesn't mean put the cuvette in, press read, wait, read, wait, read again. That's not what I'm looking for. I'm looking for making that solution all over again. So any sort of pipetting error that you have, any sort of measurement error that you could possibly introduce, any user error that you're introducing, by doing these 2 repetitions, or sorry, by coming up with a total of 3 data points, whatever difference there is going to be kind of mitigated or lost by having those 3 different trials. So let's say hypothetically, your subsequent data points are 0.495, 0.485. Well, then you could add those 3 up and come up with the average. And that average is probably going to be about 0.496, we'll say. Okay, so this is what I recommend doing, taking that unknown and getting the absorbance of that 3 times. And that means 900 microliters of the Bradford, 100 microliters of the unknown. Measure. Rinse it out. Measure. Rinse it out. Do it again. Rinse it out. Do it again. Now, with that in mind, with your known data point and this unknown, you can already provide some commentary on what the concentration of your unknown is. You can say with confidence, the unknown has a concentration less than 10 micrograms per microliter. There's not much else you can say about that. You can't say that, oh, it's exactly 9, it's exactly 9.2, because you only have one data point that you can reflect on, and that's that 10 micrograms per microliter. So what you want to do after this, so if you look at this and say, okay, well, my first trial was this, my second data point that I collected, or second time that I used my cuvette was this, third was this, and fourth was this. The 5th time that you take an absorbance reading, what you want to do is get a sample with a concentration that's lower. And let's say that you decide to go with 2 micrograms per microliter. What that means is that you have 900 microliters of the Bradford. You've got 20 microliters of your known and 80 microliters of DH2O. Now, one very important thing to remember is this needs to be very thoroughly mixed. Thoroughly mix it by taking that cuvette and tap, 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 tap to mix it up, or use your pipetteman to mix it very thoroughly. If you use your pipetteman to mix it thoroughly, you want to discard that pipette tip. So let's say hypothetically, you mix that up, you measure the absorbance, and you get an absorbance of, for 2 micrograms per microliter, 0.344. At this juncture in time, you have two data points that you can plot. Your y-axis is going to be A595, and your x-axis is going to be protein concentration. And I'm going to bracket this implying molar concentration, but we're using micrograms per microliter as our concentration. So you have two data points, 0.519 and 0.344. You can relate those to 2 micrograms per microliter and 10 micrograms per microliter. Boom and boom. Okay, with those two data points plotted, you can come up with y equals mx plus b, plug in this value right here, this 0.496, because that's a measurement on your y-axis, that's an absorbance. Plug that in for y, solve for x, and you can say what the concentration of your unknown is based on those two data points. Now, two data points, those will give you a way to, draw a straight line, but it's not going to be extremely helpful and accurate. So what you want to do with this is maybe take another data point, number 6. Let's say that we do 4 micrograms per microliter. And I say 4 micrograms per microliter because it's not really worth your time to go with 1 microgram per microliter, because where would you expect that absorbance to be? You'd expect that absorbance to be less than 0.344. So we want to get closer and closer and closer to our unknown. So let's do 4 micrograms per microliter. What that is going to consist of is 900 microliters of your Bradford plus 40 microliters of the known plus 60 microliters of DH2O. So let's say hypothetically that gets you an absorbance of 0.415. Okay, now we have a third data point, something that looks like this, 0.415, and that would be 4 micrograms per microliter, micrograms per microliter. Now we have another data point that's going to give us a unique and different y equals mx plus b. Again, you can plug in 0.496 in as your y value, solve for x, get your concentration. Now, all the while that you're doing this practical, you are not expected, and in fact, I discourage you from trying to graph while you are doing this. I strongly recommend that you simply look at the absorbances that you get, 0.519, 0.344, 0.415, and that 0.496, and say, okay, what I want to do is effectively get absorbance values that are closer and closer to that 0.496. Because if I land on 0.496 as, let's say hypothetically you did a sample that was 9.5 micrograms per microliter, so that would be 900 of the Bradford, 95 of the known, and 5 of DH2O, 5 microliters of DH2O. And let's say that ended up being 0.496. You would have a way, or without even doing a calculation, you'd be able to say, okay, well, my unknown gave me an absorbance of 0.496 as the average. My known, when I had 95 micrograms per microliter, or sorry, 9.5 micrograms per microliter, gave me an absorbance of 0.496. I think that my unknown has a concentration of 0.496 sorry. It has a concentration of 9.5 micrograms per microliter. So the point of this is to get more and more data and basically corner in your unknown value. I always kind of think about it as like, and this is a little bit of a stretch, but I have a dog and my dog likes to get out. And if I need to get my dog back into the house, what I want to do is lure my dog into the backyard. And if the dog's in the backyard, the dog's going to be like, okay, well, I'm in the backyard. Okay. I'm just going to run around because I'm a crazy dog. I'm going to look at that and I'm going to say, okay, well, I've narrowed where the dog is. The dog is in the backyard. What I need to do is I need to narrow the space that my dog is in until ultimately I can pick him up and take him inside. And so you have these known values that we start out with. You have a known concentration of 10 micrograms per microliter. That gives you an absorbance. And you can then look at your unknown and say, oh, well, my unknown has an absorbance less than 10 micrograms per microliter. It's less than this, but what is it more than? Well, I presume that it's more than 0, but you have no data to support that. As soon as you get that 2 micrograms per microliter, that 4 micrograms per microliter, that 9.5 micrograms per microliter, you're narrowing in that scope, you're narrowing in that range until you can, with a high level of confidence, say, my unknown has a concentration of this many micrograms per microliter. Okay, well, I hope that was helpful, and I hope you do well on this exam.